Okay. Thank you very much, and thank you for inviting me. It's always such a nice place, and I love to be here. Thank you. And so last year, which was online, I discussed clustering more general and talked more about Hoyle states and the Efimov effect. And today I will update, and of course I'm not going to repeat the same thing. I'm going to update you on our most recent results of our collaboration, TACSET, Texas Active Target collaboration, and essentially all of what I'm going to talk about was essentially results from last year. So, there will be three things that I'll talk about. This is the first one is going to be a role of neutrons in carbon nucleosynthesis. Also, I'll discuss clustering in near pairs in oxygen 18 and neon 18. And this is thanks to Sasha Vola, who introduced the topic very well. Will be just this experimental description of what we observed there. I think there is some interesting phenomena there. And also I'll touch on structure of beryllium-13. Before I start, let me just acknowledge contribution from many people, and the Texas Active Target Detector now has large collaboration, and we collaborate with people all over the world, from Korea to Brazil to England, Louisiana State, and these are members of my group. And actually, most of the people you see here have graduated. In fact, all graduate students who are here have graduated and gainfully employed in national labs now. So I have new students, but these were the people who contributed to the work. All right. We'll talk about different physics, but all that is united by one detector, because we did all these experiments that I will be talking about using Texas Active Target, which is quite versatile device. And let me just show you one, maybe two technical slides, and I will not get back to that ever again, so to make sure that our theory colleagues are not bored. So Texas Active Target Detector is essentially a time projection chamber, which is working in active mode, meaning that the gas which is used to detect tracks is also a target. So we inject the beam, and we essentially detect all tracks of charged particles in this active target. Over here, where you see the microchannel plate, which is highly segmented, so we can get XY position, and of course Z position is determined using timing due to a drift of electrons that are generated by the track. And this drift is due to electric field. The time projection chamber is surrounded by the shell of silicon detectors, this greenish thing here, and the shell of cesium dye detector. So we record pretty much everything. In fact, we can also detect gamma rays, but with resolution about 8–10%. We demonstrated that too. So it's very versatile device. Technical description is in this paper. And just one thing, the one last technical slide is for experimentalists. The segmentation in this detector is kind of unique in the microchannel plate in a way that we have the very highly segmented pads in the center, and there we usually use low gain. So we can have different gain regions, high gain, low gain, which is very important. The segmentation on the left and on the right is not as high. It's made by strips and chains, which is also unique for this detector. So enough of that. We've performed a large number of experiments over the last 4 or 5 years. This is the list. And as you can see, the important thing to highlight is that physics that we address with this detector is extremely broad, right? We measure neutron-induced reactions. We measured beta decay, charged particle emission, beta delay charged particle emissions. We measured fusion reactions. We measured nucleon transfer reactions. We did a number of experiments on resonance scattering. So really, this is very versatile device. Highlighting in general that active target approach is extremely useful, as you know, and provides an opportunity to do a lot with very little beam. So I'll start with the first topic for today, the role of neutrons in carbon nucleosynthesis. And this is the result that we published just recently, I think a couple of months ago. The main subject matter of this study was the triple alpha, the neutron enhancement of triple alpha reaction. So as you know, carbon-12 is primarily produced in the universe through triple alpha reaction. Three alphas come together. Actually, they first form beryllium-8 in its ground state, and then beryllium-8 captures alpha particle. And then the reaction has sufficient cross-section only because of the Hoyle state. There is a resonance at proper energy, but this Hoyle state can be de-excited by a number of ways. Right? And of course, the most common way, and everyone knows about that, this is gamma cascade. So a 0 plus goes to the 2 plus, and then to the 0 plus, 2 gamma rays are produced. Then electron positron pair emission. And another way, and of course, most of the time it decays back to 3 alpha particles. That's the dominant mode, right? First to the beryllium-8 ground state, and then 3 alpha particles. But of course, gamma cascade and electron positron pair production leads to the carbon-12 in its ground state, and this is how the universe gets most of the carbon-12. However, in some environments, there can be other de-excitation modes. And if, let's suppose if you have some equilibrium abundance of Hoyle state, equilibrium presence of Hoyle state, and lots of neutrons around. So those neutrons can interact with carbon-12 in the Hoyle state and carry away energy. So it's inverse to the inelastic scattering, right? It's inelastic scattering where neutron gains energy instead of losing. Of course, the same thing can happen to proton. If there are lots of protons in the environment, proton comes close to the Hoyle state, interacts with it, carries away energy. Same for alpha particles. In fact, this can also happen for alpha particles, lots of alpha particles, Hoyle state, and we have de-excitation. This process called neutron upscattering, and it is depicted here, right? So basically we have alpha particles creating beryllium-8 ground state. Beryllium-8 ground state captures an alpha particle, carbon-12. It is in the Hoyle state, and then neutron comes about and de-excites, drops the excitation to the ground state. Important point is that neutron can de-excite the Hoyle state to the ground state, but in other possibilities, of course, that it de-excites the Hoyle state to the 2 plus state. So the probability for that process, the cross-section, right, is not really known, and it is very hard to measure. In fact, one is impossible to measure. Look here, this is the available data for the inverse to the neutron upscattering. So this data points, the green, is the cross-section for inelastic neutron scattering to the Hoyle state, right? Which is, of course, inverse to the de-excitation of Hoyle, right? Is the inverse to the neutron upscattering. And it was measured only at rather high energies, where, of course, it is not really relevant for astrophysics, because in astrophysics, you expect neutrons of energies, well, MeV, not 10 MeV. And measurements at lower energies have not been done. And this is, it may sound strange, right? Why is that? Why we have not measured neutron elastic scattering that produces Hoyle state? Well, it's just carbon-12, right? We have neutron beams. Why it hasn't been measured? The answer is that when you work with in the neutron beam environment, in the neutron beam facilities, there's a lot of background. Neutrons scatter all over the place. They scatter from walls, from ceilings, right? From air even. And you have background. So it's very difficult to separate that background. And that's why it has not been measured at low energies. At high energies, yes, because there is very little of high energy neutron background. And there is another process, which is the de-excitation of 2 plus to the Hoyle state, right? Or the inverse is shown here. It's the inelastic scattering of neutrons on the 2+ populating the Hoyle state. This one is impossible to measure, right? Because you need to scatter neutron of the 2+ state, excited state of carbon-12. Well, there is no way to do it. But there was an argument in this paper, in this Physics of Letter paper by Mary Baird, Sam Austin, and Richard Sibbert, that this neutron upscattering may play a very important role in certain astrophysical environments. And so also there was very recent paper in Nature by Shilun Jin and Luke Roberts and Sam Austin and Hendrik Schatz that stated that also the PP, the proton upscattering, it may be very important. And essentially the astrophysical scenario there is that there is a core collapse supernova, there is a neutrino-driven wind, and there are protons and neutrons in the environment, in the shell surrounding the core collapse supernova. And there, in principle, we may have enough proton and neutron densities and enough Hoyle equilibrium abundance, equilibrium concentration, and this process may play a role. And then we get enhancement. Okay, so how do we measure it? Of course, we cannot measure the de-excitation of the Hoyle state to the ground state, but we can measure the time reverse. So this is the experimental case. So we have high energy neutron, the carbon-12 in its ground state, and then it is excited to the Hoyle and 3 alpha decay. And low energy neutron emerges. And of course, the time reverse astrophysical case is this, right? So it's the inverse to that. Okay. So, and of course, there is detailed balance principle. So if we know one cross section, then we know the other. And that's what we were set to measure. And we used the time projection chamber to do that. And to the best of my knowledge, this was the first experiment where a neutron beam was used in conjunction with the active target detector time projection chamber in active target mode. To the best of my knowledge, that was the first. So what we're set to measure is this straightforward, relatively straightforward reaction, right? We have carbon-12, which is in the gas. We use CO2, so we have carbon-12. We inject the neutron beam into the active target detector, and then what we look for are 3 alphas, which are emerging out of the blue, out of nowhere. There is no projectile track. So it's very clean, in fact, measurement, if you think about it. When we designed the active target detector, we never thought to use it in this way, but we realized that this is really very, very nice detector for that kind of measurement. We did other measurements as well with the neutron beam while we were there in the high. It was a high experiment. I'm not going to talk about that. All right, so there were some adjustments of the conditions with low pressure CO2 gas that we used, and it has to be low pressure because alpha particles that emerge from the Hoyle state, they have low energy, and we want them to propagate so that they leave sufficient. N2 is just N2 means that it's a neutron with a different energy. Correct. And 2 means that this is inelastic scattering populating carbon-12 in its second excited state, which is Hoyle state, which decays by 3 alpha particles, of course. So, like I said, we collaborated with people from Ohio, and we got a lot of help. From Zach and Carl Bruni, Zach Meisel, Carl Bruni, and students and postdocs. It was very important. So Edwards Accelerator Lab was very accommodating. They have monoenergetic neutron beam up to energies of 10, probably a little more than that, but we didn't use that, 10 MeV, right? And the important thing is that it's monoenergetic, and you can change energy in steps, and the beam is very well characterized. We use time of light, so we know the energy distribution and everything. And the energy resolution was in the vicinity of 200 kiloelectron volts. And we were getting somewhere in the vicinity of 5 times 10 to the third neutrons per second. And this is how the beam profile looks like in terms of energy, right? A different energies of neutrons. We use DD reaction to create neutrons, and we collimated them pretty carefully and send them to the active target. Special care was taken to produce very good normalization. And we used polyethylene foil and silicon detector, and then P scattering process with known cross section. So really, there were several other methods for consistency for normalization. We also had scintillator here. So I skip all these details, but normalization is very important here because we are actually measuring absolute cross section here, and that's what's important. Right? So we actually did several experiments prior to our trip to Ohio to make sure that we can measure Hoyle state, right? So what we did, we injected nitrogen-12 into the gas target. We stopped nitrogen-12 in the middle of the gas target, and we waited for the decay and observed the Hoyle states, and they are very characteristic. See this Y thing? Well, it's the alpha particle that is carrying away most of its energy, and what you see here is beryllium-8 then decays. It has certain momentum due to the decay of alpha particle, and therefore it produces this kind of characteristic letter Y. I'm not going to talk about that. There's a lot of interesting physics, which I discussed last year related to this study, and it is published in these 3 publications. What I'm going to talk about is this, right? So now we were set and ready to do this measurement, neutron upscattering. And this is how neutron upscattering looks like in the active target detector. There is nothing, and then in the middle of the detector, you see beautiful 3 alpha particle tracks. Very clean, very clear, no background. You don't care about low energy neutrons, they don't produce that because neutron has to be at least 8 MeV to do that kind of thing. Right? So it's very clean measure. And then what you do is you take neutron beam at 8 MeV, at 8.2, 8.4, 9, and so on and so forth, right? In steps, and send that beam to the active target detector and essentially measure the cross section. And I mentioned normalization. We really took great care about that. And what you see is the total cross section, this blue thing, right? It's the total cross section for inelastic scattering of neutrons populating the Hoyle state, and this is background free measurement, absolute measurement and background free. So now, of course, we also did measurements below the threshold. This is the threshold, this red line, and we saw no events. That was important check, right? And very little events above the threshold, and this is very interesting already because what you see here, this thing, this dotted line, is the prediction of Hauser-Fishbach model as used by Mary Beard in her original PRL publication. This is the prediction of Hauser-Fishbach model for this cross section, and this is what really happens. Not a surprise, right? Well, Hauser-Fishbach is a statistical model, and it reproduces cross sections more or less within 1 or 2 orders of magnitude, right? You can't expect it to be accurate. And of course, here, especially at low neutron energy, where it is important, right, for nuclear astrophysics, the cross section is dramatically lower than you would expect from the Hauser-Fishbach. There is no dramatic jump in the cross section. So it really demonstrates how important it is to have actual experimental data and not to rely on Hauser-Fishbach calculations. But that's the best they could do at the time, of course. All right, so another important feature here is it looks like resonance, right? In fact, it's not 1, it's 6 resonances. And this cross-section, we did the R-matrix analysis, and this can be nicely described by 6 resonances, 6, because we also analyzed all totality of the available data on the reactions which create carbon-13 in its compound state, right? So it was the comprehensive analysis. Before I talk about this R-matrix analysis, I want to mention that the experimental result here, which is relevant for astrophysics for this particular reaction, is independent of any analysis. Right? That's the direct measurement. So no assumptions. That's done, measured. So, but of course, we were ambitious, and we looked at all of these reaction channels, which were measured before. So the data was available, of course, for elastic scattering, NN1, the alpha N2 and alpha, and all of this, of course, leads to the carbon-13 excited states. And if you put together all this data and apply our matrix, then you can demonstrate that you only need 6 resonances to explain everything in the relevant energy region, which we did. And once you've done that, then actually you can predict this cross sections, right? The N1 N2, which is impossible to measure. It's the inelastic scattering of neutrons on the 2+ populating the Hoyle state. It's impossible to measure, but everything is now constrained, not over constrained, but constrained. So you have all the partial width to predict this reaction, which we did, which then, of course, we can also use to calculate the enhancement for the upscattering. So the way the enhancement is calculated is this formula, which was derived a long time ago and published in original paper by Mary Bird and PRL and other places as well. So the R means, R1 means no enhancement. R10 means enhancement by a factor of 10, R100 by a factor of 100, so on and so forth, right? So and have to acknowledge the huge contribution that Jack Bishop, a postdoc in my group, did. He did really marvelous job, and this is the final result. And the main punch point here, the highlight, is that enhancement is not nearly as important as previously thought. Not a surprise, right? Because the cross section is so small compared to the originally what was used for using Hauser-Fishburne calculations. Cross section small, enhancement is small. That's it, right? So, and of course, this is an important statement that this particular upscattering from the coil to the 0+ is much reduced compared to what we thought. So it's hard to imagine nuclear astrophysics scenario where it may be important. However, the Hoyle to the 2+ is way more important, in fact, and it is enhanced by about a factor of 5. And it's easy to understand why. There is a spin factor to J+1, which contributes directly, so that here is where the factor of 5 comes in immediately. And so that one is more important. This is this black line, and from the coil to the ground state, it's green line. So as you can see, the black line dominates, and the sum of them all is this one, the blue dashed curve. Okay, so let me remind you that the proton enhancement actually, it appears like proton enhancement is more important than enhancement due to neutron upscattering. All right, let me move on to the next subject. So clustering, Sasha did a remarkable introduction. So we studied neon 18 with the idea to sort of compare the data on neon 18 to oxygen 18 to try to see if the cluster states follow what we think should be the case, that the alpha spectroscopic factor should be the same between mirror systems, right? So we're studying clustering in mirror systems, and to my knowledge, this is actually the first detailed, comprehensive study of cluster states and cluster spectroscopic factors or reduced widths for the mirror systems. Lots of studies, of course, were done for about this on the systems with n equal z, right? So we know a lot, but this study really, I think, is the first one which has detailed comparison between the cluster configurations in the mirror system and also conjugate system in a detailed way. So the original idea was, and this is kind of toy model, which helps us sort of to think why oxygen 18 is interesting, because there was always suggestion, and this cartoon is borrowed from von Hertzen paper, that there are alpha cluster configurations in oxygen 18, which you can sort of think it's very naive, right? But it helps us to sort of set our mindset straight. There are shell model configurations and there are molecular type configurations, and they should be all mixed, and all those states should be present in principle in oxygen 18. Although, of course, I really don't like to think about it this way, because the real physics is far more complicated, and we cannot really just put states in one or the other category that easily. Anyway, the important thing is that on oxygen 18, there was a lot of experimental data, a lot. And what I'm showing, showing is just a subset, and the detailed thermometrics analysis for carbon-14 plus alpha was made, right? And we have the Armetrix feed with the partial widths and states and everything. And I'm not going to dwell on this picture, but we have the data. So now we move toward neon 18. And the difference between oxygen 18 and neon 18, of course, you expect these are mirror states. So, the same states you should observe, they should have the same spectroscopic factors and all that. But the dynamics is very different, right? The decay thresholds are very different. Therefore, influence of the continuum is very different. And thanks to Sasha, you sort of already know what to expect and what kind of differences there may be. Are there any? That's the experimental question, or can we observe them? So this experiment was done at Texas A&M University, and we used oxygen 14 beam. We used our Mars momentum achromatic flow separator to produce oxygen 14, 50 MeV, 10 to the 4th, pretty clean. Well, these are just, this is the slide that shows how we select the elastic scattering events, because that's what we're measuring. We're measuring excitation function for resonance elastic scattering of oxygen 14 on alpha particles. And the selection is very clean. The data is backgroundless. Without skipping, I'm going to skip the details, but essentially you select alpha particles, you feed the tracks. This is alpha particle, this is the projectile track, you get the angle, you get the location of the interaction, you plot it on the special plot, alpha energy versus interaction point, and the kinematic banana for elastic scattering is clean. So you have it there. So we have the spectrum. And this is in comparison with oxygen 18. Obviously, it looks different, but similar. And what we did is we took the parameters for our metrics for oxygen 18, and we converted that directly to oxygen 14 plus alpha data. And then, of course, we had to do a lot of modifications, right, to feed the spectrum. But the blue line, I'm sorry, I don't think you see it very well, but there is a blue line that goes through the data points. And of course, as you can see, the statistics is much lower as compared to oxygen 18 case, not surprisingly, because carbon 14 is a stable, well, it's not stable, but it is. We used it as a stable beam at Florida State. And here at Texas A&M, of course, for oxygen 14 is radioactive beam, so its intensity is 6 orders of magnitude low. But active target detector allows us to do this kind of measurements with 10 to the 4th. So the feed was done, we have the result. I'm not going to show every state and discuss all that. I'll just give you small highlights and the punchline. One highlight is that there is 0+ scattering feature. Right? I changed the slide yesterday. So now we have the scattering feature. We have observed this scattering feature in oxygen 18, which manifests itself as a very broad 0+ state, extremely broad. And this is the phase shift. In fact, what is shown is the square of the sine of the phase shift. And this is how it behaves. It never gets to 1 for oxygen 18. We see exact same thing in neon 18. And without that, we cannot feed the data. And this is how the phase shift looks, or the square of the sine of the phase shift looks like. In fact, we compare it to the potential model predictions. And of course, potential model takes into account the continuum very nicely, as Sasha pointed out, automatically, of course. This is the prediction of the potential model when you use the potential between alpha and oxygen 14. This is what it does, right? So essentially, it's very essential feature. You cannot feed the cross-section without it. But maybe it's not a state, right? And the phase shift only goes to, well, you see, it's not 1, it's the 0.17. But it's very important. It has to be there. In fact, if it is not there for oxygen 18, there is this dramatic picture. If it is not there, you see the blue. If it is there, you see the red. The red feeds the data, the blue does not. So this is how it manifests itself. The 6+. The reason it is important is, well, it's the high spin states we observed, and look at the comparison between the two, right? So oxygen, pretty much 1-to-1 to neon, two very strong 6+ states. That's what we see, two very strong 0+ states. Great. Spectroscopic factors look similar, but different, right? And this is quite interesting also that there is an indication of yet another 6+, which was not observed at oxygen in oxygen 18. But yeah, let me skip that because I don't have that much time left. So just remember this picture, and across the board, this is how it looks like. There are strong states in oxygen 18 which correspond to neon 18. There is a very good correspondence. So we have that. Spectroscopic factors are not exactly the same. Sasha talked about 1- state IMO states. I'm not going to do that. So I have to acknowledge contribution of Marina Barbu, who spent more than a year, 2 years, I think, fitting this. This is very difficult procedure, believe me, because you fit and then you refit and then you make sure that you included all the states that need to be there and you do not include those that do need to be there. And so we went back and forth. Okay, but now we submitted the paper. It's under review in PRC. Here's the punchline for this. This is a very important plot, which essentially demonstrates what Sasha mentioned in his table, but this is a sort of graphically demonstrates it. X-axis is the ratio between the width of the big state, larger width, to the small. On the y-axis is the ratio of the reduced widths, spectroscopic factors, alpha spectroscopic factors. What do you expect to see? You expect to see 1 all the time. Of course, we have experimental error bars, and we take great care to really produce reasonable error bars there. This is the experimental error bars. Of course, they should scatter, but they should scatter around 1, randomly more or less, but essentially it should be 1. That's not the case. So the bigger state, essentially, when we have the bigger state, it always has enhanced spectroscopic factor. Not by much.
I'm sorry, I didn't get what you call bigger state.
Bigger state means its width, literally. Width is bigger than the width of this one. Width is larger, right?
It's broader.
Broader. Yeah, it doesn't have to be very broad. It's broader state. And the ratio, if the ratio of the width is more than 1, then what you get is the ratio of spectroscopic factors also. And this is not trivial at all, because we have all these different thresholds and penetrability factors and all that. I'm not claiming that this is absolutely definitive result. Way more studies have to be done here, and error bars have to be reduced, obviously. This is something that is very interesting, completely unexpected. I credit Sasha for that because I have not noticed that. He did. All right. So highlights for this part is that, so I think it is the first detailed study, large scale comparison of cluster states in mirror pairs. So there is a direct link between the cluster structures in mirror nuclei, as expected. That's not a surprise. But there is there is evidence, I should not say clear, but there is evidence for a systematic difference between the mirror systems. And one explanation may be this coupling to the continuum and the superradiance effect that Sasha mentioned. Not claiming that definitively, right? More studies have to be done. Error bars have to be reduced. Maybe some other methods have to be used. More statistics is needed. This is something interesting that we need to look at. All right. So how much time do I have? Like none.
Oh, okay.
Okay.
Now, if you want more time, you are taking it from the question.
Okay. So how much time do we have for questions now?
To say it frankly, now we are not with the fixed hours of the coffee break, so there will be a discussion session after.
Yeah.
Okay.
So you can
Okay.
work on this and then.
I'm going to do this, right? I'm just, because I think this is quite interesting result on beryllium-13. So I'll just mention few highlights. I'm not going to go into details, right? So beryllium-13 is an exciting system because frankly, we don't know what is the structure of the low-lying states there. But even we don't even know what is the ground state spin parity. And it has to do, of course, with N=8 shell closure there or lack of thereof. And of course, there is a history of beryllium isotopes which behave in an interesting way with the parity inversion for beryllium-11 and so on. Experimental situation for beryllium-13 is complicated. And there are lots of experiments that have different number of states available and different spin parity assignments. So we try to resolve this situation and to see if we can really put a nail into the coffin of this question. I am not saying that we did, right? But the idea was that we just measure elastic scattering of beryllium-12 on protons populating the isobaric analog states of beryllium-13, resonance elastic scattering experiment. And that's what we did. So we demonstrated that it works very well for the A=9 mirror system. Not going to go into details of that, no time for that, but it works, right? You can answer questions later. The experiment was performed at Triumph, and the intensity of beryllium-12 beam was very low, 500 particles per second. Yet we were able to do the measurements, right? Here's the result. And look at this picture. So this is the excitation function for protons, for elastic scattering of protons on beryllium-12. The spectrum is completely dominated by the T=5½ isobaric analog states. You just put two, the 1/2 plus here and the 5½ plus, and you describe the spectrum. In fact, this picture looks essentially identical to fluorine-15. Remember, I think Nicolas Michel showed the picture of oxygen-14 resonance elastic scattering on protons. And that spectrum is dominated by 1/2 plus state and 5½ plus state. That's what we see. It's essentially identical.
Those assignments are, of course, in parentheses. This 1/2 plus and 5½ plus.
Yeah, how could you
How
get
do
this?
how can you get this number?
Very good. Yeah, here. So if it is, so first of all, the shape and the cross section. The cross section, sorry?
Yeah, the statistics may not allow to get it with the shape. Yeah, go ahead.
Yeah, right. But look here, right? So say if you replace 5½ plus with 3½ plus, then you get the blue instead of the red. 3½ plus has a lower cross section, and cross section is fixed by the essentially proton and neutron widths, and neutron width is related to proton width with isospin Clebsch-Gordon coefficients. We assume isospin conservation here. So this has to be the 5½ plus. I'm absolutely sure about that. And the 1/2 plus is the interference pattern. By the way, this is angular distribution. This is at different angles, right? And if you make an assumption that 1/2 plus is 1/2 minus, then you get a totally different, just completely different interference. It is not 1/2 minus what we see. I'm not saying that there is no 1/2 minus there. I do not make this statement, right? What I'm saying is that to describe the spectrum, it is sufficient to have 1/2 plus and 5½ plus, right? Sufficient. All right, and this is the spectroscopic factor is very small, apparently, 0.2, of course. That we measured that we have widths and the reduced widths, and that is another indication that there is no N=8 shell gap there. It's just the 1/2 minus P1/2 is very close. They all mix, and the spectroscopic factor is rather small for 1/2 plus. All right. So since I ran out of time, me get to the summary. And so as you can see, we really wide range of experiments can be performed. And I highlighted just 3 of our recent results on beryllium-13 on mirror systems in A=8. clustering and mirror systems, and also the neutron upscattering result. Thank you.